Hi.
Welcome back to this lecture series on deep learning. In this lecture, we will discuss about the introduction about what is autoencoder and generative models in machine learning. First, we should know what is an autoencoder. Autoencoder is a type of is an unsupervised neural network that learns efficient representation of input data by compressing it into a lower dimensional form and reconstructing it to backer. So that means an autoencoder is a type of an artificial neural network that learns to represent input data efficiently without requiring a labeled training example. Without requiring labeled means it is an unsupervised learning. It compresses the input into lower dimensional representation called the latent space and then reconstructs the original data from this compressed form. The primary goal is to learn meaningful patterns and features while minimizing reconstruction error. And the key objectives of the autoencoders are feature extraction. Feature extraction is the process of identifying important characteristics from raw data. Autoencoders automatically learn these features without manual intervention, making them useful for machine learning tasks where meaningful patterns must be identified from larger data sets. And the dimensionality reduction means it reduces the number of input variables while preserving important information. Autoencoders compress high dimensional data into a smaller latent representation, helping to reduce storage requirements and computational complexity. Next, data compression. It involves representing information using fewer bits while retaining essential content. Autoencoders achieve compression by learning compact representations of data that can later be reconstructed with minimal information loss. Noise removal is the process of eliminating unwanted disturbances from data. Autoencoders, especially denoising autoencoders, can reconstruct clean signals from noisy inputs, improving data quality and reliability. Next, representation learning. Representation learning refers to automatically discovering useful features from data. Autoencoders learn hidden structures and relationships within datasets, enabling more effective machine learning and data analysis. The applications of autoencoders are image compression, medical image analysis, anomaly detection, and recommendation system. Image compression means autoencoders are used in image compression by reducing image size while preserving visual quality. This helps save storage space and reduces transmission bandwidth requirements. And medical image analysis. In healthcare, autoencoders assist in analyzing medical images such as X rays, CT scans, and MRIs. They help identify abnormalities and enhance image quality for better diagnosis. Anomaly detection means autoencoders can detect unusual patterns by comparing reconstruction errors. Data points that produce high reconstruction errors are often considered anomalies or outliers. Next, recommendation system. The autoencoders are used in recommendation systems to learn user preferences and item characteristics. This enables personalized recommendations in platforms such as e-commerce and stream services, etc. And the architecture of the autoencoder consists of three main parts: encoder, bottleneck, that is latent space, and decoder. So the encoder, the function of the encoder, it is responsible for transforming the input data into a compressed representation. It progressively reduces the dimensionality of the data while preserving important information needed for reconstruction. Next, It compresses the input data into latent representation means the encoder converts complex input data into a compact latent vector that captures essential features. This representation serves as a summary of the original data and reduces the dimensionality means by reducing the number of features, the encoder eliminates the redundant information and focuses on the most significant patterns within the data. Next, bottleneck, we can call it as latent space. The bottleneck is the central layer of the autoencoder. Here I'll show it to you. This is the central layer of the autoencoder where compressed information is stored. It forces the network to learn efficient representations of the input data and store as compressed information. The latent space contains the compact version of, see here, the latent space. The latent space contains the compact version of the original data. It retains important characteristics while significantly reducing the data size, and it contains the essential features. Only the most informative features are preserved in the bottleneck layer. This layer, uh, it enabling efficient learning and reconstructions. Next part is the decoder part. The decoder reconstructs the original data from the latent representation. It reverses the compression process performed by the encoder. Reconstruct original data from the latent representation means using the information stored in the latent space. Here the data will be stored. The decoder attempts to reproduce the input data as accurately as possible. Whatever the data we are sending, it has to be reconstructed from this layer. And the next input to the encoder to latent space to decoder, and then we have to reconstruct the output. This workflow represents the complete functioning of the autoencoder. Data is compressed, stored, and reconstructed while minimizing the information loss. So this is the diagram of the autoencoder. Here we have got encode. This part is the encoder part. This is the bottleneck or latent space, and this part is the latent decoder part. See here you will have the encoder like this, and this is the latent space that we can call it as the hidden layer, and this is the decoder part, just opposite to this encoder. Here we are compressing it, and then we are reconstructing the data. And the working of the autoencoder, first step is the input data is fed into the encoder. The process begins by supplying input. Here we are giving the input data to the encoder. The input may be images, text, audio, or other form of the structured data. Next, encoder compresses the data into latent representation. The encoder extracts the important features and converts the input into lower dimensional latent vector. Next, latent vector stores the important features. The latent vector acts as a compressed summary of the original input containing only the most relevant information. Next part is the decoder part. Decoder reconstruct the data. The decoder uses the latent space to recreate the original input data. Reconstruct an error is also been calculated. How means the reconstructed output is compared with the original input to measure the reconstruction error. Suppose if I am sending here 5, I should get the 5. If I am not getting, instead of 5, 4.5, what is the error? 5 minus 4.5, 0.5 is the error. So we are going to, like that, we are going to calculate the error. Next, weights are updated using back propagation. That is, the network adjusts its parameter using back propagation to reduce reconstruction error and improve performances. So this is the workflow of the autoencoder. So these 6 steps. Next, loss function means the loss function measures the difference between the original input and the reconstructed output. Minimizing this loss helps the autoencoder learns accurate representation. And these are all the types of autoencoders. Basic encoders, sparse autoencoder, denoising encoder, contractive autoencoder, variational autoencoder. The basic autoencoder consists of standard encoder decoder architecture that learns compressed representation and reconstructed input data like this. And next is standard encoder, and that is here we are having the, that is standard encoder decoder structure. This means the structure includes an encoder for compression and decoder for the reconstruction, forming the foundation of autoencoder model. Next is sparse autoencoder. A sparse autoencoder enforces sparsity constraints, ensuring that only few neurons are active at a given time. And it encourages the sparse activation. By limiting the active neurons, the neural network learns more meaningful and specified features and learns meaningful features. Sparse representations often capture important pattern and improve feature extraction performances. Next to denoising autoencoder, the denoising autoencoder learns to reconstruct clean data from noisy input and it removes the noise from the corrupted input. It improves the data quality by eliminating distortions and restoring original information. Next, contractive autoencoder. Contractive autoencoder increases robustness by reducing sensitivity to small changes in input data and it improves the robustness. They produce stable feature representation that generalize better to unseen data. Next one is the variational autoencoder. Variational or probabilistic model capable of generating entirely new data samples. It generates the new samples. VAE, that is variational autoencoders, can create realistic synthetic data by sampling from learned probability distributions. Next, probabilistic learning approach can be used. Instead of learning fixed representations, VAEs, variational autoencoders, model data using probability distributions and enabling generative capabilities. Next, the important type is variational autoencoder. What is VAE? A variational autoencoder is advanced type of autoencoder that combines deep learning with the probability theory. Unlike traditional autoencoders, which learn fixed latent representations, and VAEs learn probability distributions of data. This allows them to generate new samples that resemble the training data while maintaining diversity of realism. And the main features are probabilistic latent space, generates unseen samples, smooth latent representation, useful for image synthesis. Probabilistic random space means in VAE, the latent space is represented by probability distributions rather than fixed values. Each input is encoded as a mean and variance, enabling the model to sample different latent vectors and generate diverse outputs and generates unseen samples. One of the major advantage of VAE is their ability to generate entirely new data samples that were not present in the training datasets. These generated samples retain characteristics of the original data while introducing new variations. And the smooth latent representation means the latent space learned by VAE is smooth and continuous. Similar data points are located close together, allowing smooth transitions and interpolation between different samples. And as it is used for its image synthesis. Means VAEs are widely used for image synthesis because they can generate realistic images by learning the underlying patterns and structures present in the image datasets. And the main applications of VAs are face generation, medical imaging, and data accommodation, drug delivery. Face generation means VAs can generate realistic human faces by learning facial features from large data sets. The generated faces often appear natural despite not belonging to real individuals. Medical imaging, it is being used. In medical imaging, VAs, variational autoencoders, are used to generate synthetic medical images for training diagnostic models and supporting healthcare research while maintaining patient privacy. Data augmentation. VAEs helps increase dataset by creating additional synthetic samples. This improves machine learning performance, especially when available training data is limited. Next, drug delivery. In pharmaceutical research, VAEs assist in generating new molecular structures and identifying potential drug candidates, accelerating the drug development processes. Next, the introduction about this is the interpolation of the variation autoencoder. Here, image one encoded, we have to encode it. This is being stored in the latent space, and we have to reconstruct the image in the decoder part. Next, we'll see the introduction about the generative models. The basic definition for the generative models are machine learning. These are all the machine learning models designed to learn the probability distribution of data set and generate new data that resembles the original training data. They focus on understanding how data is created rather than simply classifying it. The main goal is the primary goal of the generative model is to learn the underlying data distribution so that realistic and meaningful synthetic samples can be produced. And learn P of X, that is probability distribution of data. Generative models estimate the probability distribution P of X, which represents how data is distributed within the data set. Understanding this distribution enables the model to generate new samples with similar characteristics. And image generation. Generative models can create realistic images such as faces, landscapes, artwork, and objects, etc. This capability has revolutionized digital content creation and computer vision applications. Next, text generation. Text generation model produce human-like text by learning language patterns from large text corpora. Examples include chatbots, virtual assistants, and content generation systems. Speech synthesis. Generating models can generate natural surrounding speech by learning voice characteristics and pronunciation patterns, enabling applications such as virtual assistants and audiobooks. Next, music generation. Music generation systems use generative techniques to compose original that is melodies, harmonies, and rhythms based on learned musical structures. Video creation. Generative models can generate synthetic videos, animate characters, and create realistic visual effects for entertainment, gaming, and simulation applications. And the types of generative model, this and all we'll discuss in the later lectures. Just we'll see the types. Variation autoencoders, as we have seen, generative adversarial networks, a diffusion model, auto-regressive model. Here it will uses the probabilistic approach, and it is the VAEs use probability distribution to represent latent variables, allowing them to generate diverse and realistic inputs. And fast training compared with some other generative model, VAEs generally have stable and efficient training processes, making them easier to implement and optimize. Generative adversarial network. GANs consist of two neural networks that compete with each other to generate realistic synthetic data. And generator and discriminator. The generator creates a synthetic samples while the discriminator evaluates whether the samples are real work or fake. Their competition drives continuous improvement. It will produce the high realistic output. GANs are known for generating extremely realistic images, videos, and other forms of data that can closely resemble real-world content. Diffusion model. The diffusion model generates data by gradually removing noise from random inputs through a series of refinement steps. State-of-art image generation. Diffusion models currently achieve some of the high-quality image generation results and are widely used in modern AI systems and is used in modern AI image generators. Many advanced image generation are really on diffusion models due to their ability to create detailed and realistic visual content. Next, auto-regressive model. These are all the types of generative model. Auto-regressive model generate data sequentially, predicting one element at a time based on previously generated elements. It generates the data sequentially. Each output is generated using information from earlier outputs, ensuring logical consistency and coherence. And the common and language model. Auto-regressive techniques are widely used in large language models for text generation, translation, and conversational AI. Next, generative AI adversarial network GANs. The generator is a generator. Generator is a neural network responsible for producing synthetic data sample from random noise. Its objective is to create outputs that are indistinguishable from real data. And it creates a fake sample, means the generator continuously improves its ability to create realistic synthetic data that can fool the discriminator. Discriminator distinguishes the real and fake examples, and the training process what we have used in this case is the generator we are going to train it, and it will be a dual process. um, Correct. Generator discriminator competition means GAN training is based on the adversarial process where the generator tries to fool the discriminator while the discriminator attempt to correctly identify fake sample. This competition improves both network over time, and the main advantages of the GANs are high quality image regeneration, realistic output. GANs can the main applications are GANs are capable of producing high resolutions and visually appealing images with remarkable realism. Realistic outputs, that is, the adversarial training process enables GANs to generate outputs that closely resemble real world data. And the applications of face synthesis, deepfake creation, image enhancement, art generation. Face synthesis means GANs are widely used to generate realistic human faces for entertainment, research, and digital media applications. Deepfake creation means GAN's technology enables the creation of synthetic videos and images where faces or voices are realistically modified. Next, image enhancement. GANs improve image quality through tasks such as super resolution, restoration, colorization, and noise reduction. And art generation also, it is being used. Artists and designers use GANs to create innovative artwork and creative visual content. So the applications of so this is the process of GAN. So here training data samples discriminator and then discriminate loss generation loss, and the error is being occurred back propagation algorithm. We are going to use it. The applications of autoencoders and generative models or autoencoder applications are it is being used in image compression, feature extraction, fault detection, data and denoising, and healthcare diagnostics. And the generative model applications are AI image generation. That means generative image models create realistic images, as I said already, for digital content creation, entertainment, and design application. Chatbot and LLMs, generative AI models, power model conventional AI systems capable of understanding, generating human-like responses. And speech synthesis. Generative models enables realistic voice generation for virtual assistants, navigation systems, and accessibility tools, and it is being also used in the drug delivery. Generative AI accelerate drug development by generating novel molecular structures and predicting their properties. And synthetic data generation means organizations use synthetic data to train machine learning model when real world data is limited and sensitive. And the industrial applications are manufacturing. Generative and autoencoder based systems improve quality control, predictive maintenance, and process optimization. It has been used in the finance also. Finance institutions use these models for fraud detection, risk analysis, and customer behavior predictions. And is also used in the healthcare. Healthcare applications include medical image analysis, diagnosis support, and personalized treatment planning. And the cyber security, that is generative models and auto help detect anomalies, cyber threats, and unusual network activities. And autonomous vehicle, it is being also used. Self-driving vehicles use these technologies for perception, object detection, and environmental understanding. So these are all the advantages and limitations. Advantages are efficient feature learning, dimensionality reduction, generates realistic synthetic data, reduces manual feature engineering, and supports unsupervised learning. And the limitations are, even though it has got some advantages, it has got limitations also. High computational cost. Training deep generative models often requires significant computational resources, memory, and processing power. And the training instability. GANs can be difficult to train because the generator and discriminator must remain balanced throughout the learning process, and large data set is required. High quality results typically require large and diverse data sets for the effective training. And the risk overfitting, another limitation is models may memorize training data rather than learn general patterns, reducing performance on unseen data. And it is difficult for hyperparameter tuning. Selecting optimal learning rates, network architectures, and training parameters can be challenging and time consuming. Coming into the conclusion, Autoencoders learn compressed representation data. Autoencoders efficiently compress data into compact latent representation while preserving important information for reconstruction. So the next one is the encoder extracts and compresses the feature while the decoder reconstructs the original data, forming the foundation of automatic autoencoder systems. Next, variational autoencoders. VAEs introduce probabilistic learning mechanism that enable generation of new synthetic data samples. The next point is generative models create new realistic samples, right? It will create a new closely resemble the original data sets. And GANs and diffusion models are powerful generative techniques. GANs and diffusion models represent two of the most successful approaches for generating high quality synthetic data. Next application is these technologies are transforming numerous industries, enabling intelligent decision making, automation, and creative content generation. So, next, the future scope of this GANs and autoencoders are generative AI. Future developments in generative AI will enable more advanced content creation, automation, and human computer interaction. Digital twins. Digital twin system will use generative technology to simulate and optimize real world processes and environments. Next, smart healthcare. Now, future healthcare solutions will leverage generative models for personalized medicines, diagnosis, and treatment planning. Next, autonomous system. Generative AI will enhance the intelligent and adaptability of autonomous robots, vehicles, and industrial systems. Next generation content creation. Generative technologies will continue to revolutionize content creation by producing realistic images, videos, music, and interactive experiences with minimal human interventions. Hope everyone understood about the basic concepts about autoencoder and GANs. The remaining things we'll discuss in the next lectures in detail. Thank you.